Okay, today we're finishing up 1.8. As a part of that, I've got some of the equations written up here. So if you need to pause a second to write things down, make sure you do. But this is looking at example 7. And we're looking at where is this greater than or equal to 0? So x minus 3, square root of x plus 1. So this is 0 when either of these factors are 0. So when x minus 3 is 0, that's 3. When square root of x plus 1 is 0, that's -1. Now, taking a look at this, my domain, I can't have a negative square root. So -2 would give me a negative in the square root. My domain only goes from 1 to infinity. So as I talk about when this is greater than 0, I can't have anything less than -1. I'm going to make a sign plot here, and I'm only going to start at -1. There's nothing left of that. So when I plug in my range, remember for a sign plot, I pick a value between -1 and 3 because the sign doesn't switch in those regions. Take my value between -1 and 3. Let's do 0. 0 gives me a negative in the first factor, positive in the second, giving me overall a net that's negative. Pick something to the right of 3, like 4. 4 minus 3 is positive. Square root of 4 plus 1 is also positive. That gives me a net positive. The question is, when is it greater than 0? So looks like greater than or equal to. So I have to include 3. So the 3 to infinity range is there. I really would like it in interval notation. Yes, this x is greater than or equal to 3 is correct. But the interval notation, that's the answer that I'd like. Let's take a look at the graph quickly. And we'll verify that we get the same result. And what you're not seeing, the TI-84 here, should actually go all the way to here. That graph does go all the way there. It is greater than 0, meaning the y-coordinate is above 0. Goes above 0 here, that's 3 to infinity based on, again, I map based on x's. Okay? Oops, I already had this one. Okay. This, example 8, we're looking at less than 0. Again, I look at my zeros and my vertical asymptotes. My vertical asymptote for the bottom is -3. My 0 on top is 2. So those are the two things I have to put on my sign plot. Those are the two spots it could potentially switch signs. Either has to be a 0 where it crosses the x-axis, or a vertical asymptote where it could jump across. None of these functions have jumps in them. So let's start with over here to the left of -3. We'll do our sign plot again. -3 plus square root of -4 minus 2. Let's do that first. Is a negative. The square root of, or the absolute value of -4 plus 3. -4 plus 3 is -1, but the absolute value is positive. Hey, absolute values are always positive. So that will always be positive for the bottom, giving me a net negative, which is in my region. We'll do 0 here. 0 minus 2 is negative. Again, absolute value is positive, giving me a net negative. And when we cross x minus 2, we get 3 minus 2 is a positive. Let's write that neater. And That's a positive over a positive, and that gives me a net positive. So my results, I'm looking for when it is less than 0, so it's looking at these negative regions. That's the, hold on, my drawing's not working. There we go. It's those chunks. Now I can't say negative infinity to 2 because -3 is a vertical asymptote. I cannot include that. That's not part of my domain. So I need to have this break here, negative infinity to -3, but I don't include -3. -3 to 2, I am going to include 2 because that's a 0 and it could be equal to 0. Okay. That's a little, yes, I am getting a little technical. This, if I'm looking at it on a number line, I have this hole here. I come up to +2, and I've got this closed circle because it isn't or equal. But it can't be equal to a vertical asymptote, so that still has to be not there. Let's take a look quickly at the graph here of this one. So here's a little trick for turning on and off graphs. I entered all of them ahead of time. You can turn a graph on and off by having the equal sign highlighted. And all I'm doing is pressing enter over the equal sign. And we can see below 0 on this graph comes to here. It's everything over here, but I'm taking out my vertical asymptote. And my vertical asymptote being -3. Okay, we got a couple more examples. One of them here is the standard box problem. We've done this several times already this year, but we're taking a sheet of cardboard, we're cutting a corner out of size X. The total dimensions of the cardboard are 25 and 20, giving us a volume of height X right there. Length 25 minus 2x, because I'm cutting it from the corners, with 20 minus 2x. Okay? So that gives me my volume equation. The question asks me, when is that volume greater than 600? And this is one that I'm going to need to solve with the calc. Well, I suppose I could solve it by hand. It's probably possible. No, it's going to be a cubic. So pretty much this is a cubic because I've got x times x times x. So I pretty much can't solve this by hand. So I'm going to go to the graphing calculator. And I'll go back to my y equals. I'll switch which graph I've got turned on. That's the third one. I also need to set in here 600. I know when I'm thinking about domain here, when I think about my domain, 20 minus 2x is a width dimension. It cannot be less than 0. So the smallest it could ever be is 0. The length dimension could be a little bit longer, but then you'd have a negative width, and that doesn't make any sense. So this happens when x equals 10. So I'm going to think about that when I set up my window on my calculator. We'll go 0. We don't have any negatives. But my x max is 10. My y min will go 0 again. Since I set in 600, I'm just going to go 1,000 and have something bigger. And I think it looks better if your scale is about a 10th to a 50th. At most a 50th. 10th. Usually I do a 10th to a 20th of the y max. Okay, so I'm looking at when is it larger? That's functionally looking at when is it larger? That's this region. Now I'm going to have to go use my intersection tool Find the intersects. Okay, I'm gonna write that down. That's my upper bound. It was a greater than or equal to, so these are inclusive, 6.159. I'm gonna keep 3 decimal places. That's what I'm expecting you guys to keep. Let's find our other intersection. Again, to get that intersection, I just make the guess closer. 1.659. And that is my interval where it is greater than 600. Okay. So my box will have more than a volume greater than 600 if X is between 1.659 and 6.159. If that's what I need, more than 600, that's fine. I could find the maximum. What is the largest volume I can have? So I'm going on the left curve and just finding its max. I don't care what the guess is, it's between there. So if I cut out something of 3.681, it doesn't give me, oh, it's inches. Inches from the corner of these pieces of cardboard, I will get my maximum volume. What is my maximum volume? My maximum volume is the y coordinate, 820. This is the dimension that I'm cutting from the corner, 3.681. I'm going to go back to that box and point at the 3.681. That's this right here. The 3.681 is the x I'm cutting out of the corner. Okay, we have one more example. It's a continuation of one from 2.7, where we had, here it is, the volume. And this is the equation we're going to end with. I'm going to show you how to get it again. We had a 2-liter can, and we were trying to find its surface area. Okay? So this is my 2-liter can. I know a can is a cylinder. That's pi r squared h. I'm going to solve this for h right away because I need to. I showed this earlier, but I'm going to probably a good thing to review. Okay, we're trying to find a surface area less than 1,000. So I need to write a surface area equation for my can. So a can is a cylinder, has a top and bottom that are circles. Those circles are 2 pi r squared. There's 2 of them, so that's why it's 2. Pi r squared is each circle. Let me grab a sheet of paper for the going around. This is my, okay. Given you this illustration before, but here's my can. Looks like a cylinder. This, I don't have a top for this, but when the side unwraps into a rectangle. Area of a rectangle is length times width. Length is here on the bottom, and that's the circumference of the circle. Width is height. I want circumference, I don't want pi d, because that introduces a new variable. I want 2 pi r. So twice the radius times pi, same as pi times diameter. So this is length times width. I know I want my surface area to be under 1,000. So that's 1,000 is greater than. And now I'm going to substitute in my height variable. And I can do a little canceling here. I got a pi that cancels. I got an r that cancels with this r squared, leaving me in 2 times 2,000 is going to be 4,000. Okay. Again, to solve this, we're going to use a graphing calculator. I could multiply both sides by r to try to solve it by hand, but then I end up with a cubic. And we solve cubics by graphing calculator. Methods for solving cubics that don't factor are way beyond this course. And I don't even remember how to do them. It's been far too long. So we'll go back to our y equals. Turn this one off. Turn this one on. And I'm going to switch this to 1,000. Probably need to make my window. I don't know if I'm within 10, so I'm going to go 20 for my x's. And since I'm at 1,000, I need to go at least bigger. So 1,500. 100 is still fine. That's in the 10 to 20 range for the scale. So the scale tells me how close these lines are together on the bottom. Hold on, let me grab the pen so I can mark on it. How close those are together. If your scale is too small, they just end up being on top of each other. It's like a solid line. It's not always a huge deal, but it's a little easier to read a graph when they're nicer. So it asks for less than 1,000 for surface area. So really, I'm looking at this region down here. Again, I got to find my intersects. Oops, that's not the one I want. I want second calc and find my intersects. Okay, my upper boundary. This one was a less than. It was a strictly less than. So I'm not going to include it. 9.655. So I'm going to 3 decimal places and I'm rounding there. That's when it equals 1,000. That's what we thought. Okay, let's find the other intersection. Yep. 4.619. So anything between there will have the surface area of the can be less than 1,000 square centimeters. Again, we could find a minimum. If it asks me for the minimum, we just find that point using the minimum function. And that is the end of 2.10. Okay.